In this section, we are going to start exploring performance issues with blockchains, and we will investigate various approaches in which blockchain systems have tried to improve performance. A lot of the ideas actually will sound very familiar to many of you database people who have worked in infrastructure, because performance depends a lot on the amount of concurrency, parallelism that we can achieve while accessing data. And as you know, there are traditionally pessimistic approaches and optimistic approaches. So in the pessimistic approach, you lock stuff first. For example, if I'm using two-phase locking, so you ensure the order in which transactions are going to be executed before you execute a transaction. Once I've obtained all my locks, I know that the execution will be correct and serializable, consistent, and all of that. On the other hand, we have optimistic approaches where you optimistically assume that there is no conflicts. You execute the operations and then verify, validate later on that conflicts did not occur that are going to violate the order that in which the execution was made. So the ordering is done afterwards. So what we're going to see here is how the same philosophy was actually implemented in various permission blockchain systems. So we have two things we have to worry about: the order in which operations are executed, the order without executing them, and then the execution. So those are the two main phases. You can order first, i.e. a pessimistic approach, and then execute. And there are many examples of this. For example, tendermint, quorum, chain core, multi-chain, etc. Or there is the optimistic approach where you execute first and then order and validate that the order that you got is consistent with the execution order. Finally, there is an approach which is also pessimistic, which is the order parallel execute. And in that case, you order, but you extract enough information about the relationship between conflicting operations so that when you execute them, you can execute them in parallel. And this is the approach which was used in Part blockchain. So let us start with the order execute. In this case, we have a set of clients, a set of orders, and a set of executioners. The blockchain is replicated among the executioners based on whatever criteria you might have. So you have different applications, you have a supply chain, etc. You might have different reasons for having a different number of executioners. The order is independent, and that depends on your underlying failure model. If we're going to assume malicious failures, then we at least require a 3f plus 1. So if f is equal to 1, then I need 4 orders to overcome potentially malicious behavior of one node. So you have to know the underlying assumptions about the system. Clients issue transactions. Each time a transaction is issued, it is sent to the orders to find an order in which consensus is maintained, is achieved to order these various transactions. Once you have a block or enough transactions, depending on a notion of epochs or a notion of the size of each block and how many transactions are going to fit into a block, you take this block and it's been ordered, you send it to the executioners. Now, what do the executioners go? They go sequentially through each of these transactions that are in the block and execute them one at a time. Once they are done, we are finished of course, the challenge here is that you are executing the transaction sequentially, one at a time. And this was kind of the whole reason why we moved from serial execution in a regular database system. We developed concurrency control protocols to achieve serializable behavior. So, but this is the basic model for the order execute. And a good example of this is Tendermint. And Tendermint uses PBFT, so Byzantine fault tolerance. Now, you have a lot of nodes in the system, so you want to ascertain or to determine who are going to be the orders. So they use a notion which is actually borrowed from the permissionless world, which is called proof of stake. In proof of stake, a node can act as a miner or validating transactions according to the amount of wealth that it has, so according to the amount of coins that it has. And when a node participates in a consensus protocol, it takes these coins and deposits them in a bond. So this kind of restricts that I cannot keep using this amount of money all over again, and the orders become the same. An order then has voting power that corresponds to amount of bonded coins that it has. So if I'm very rich, then I have a lot of power in my voting assets during this particular ordering behavior. The protocol is actually PBFT, so it goes through the cycle. I will not go through this flow chart that indicates things, but basically you need to acquire quorums, and because this is PBFT, you need 2/3 majority, and the voting is not based on one side being equal to 1, but rather one side is equal to the amount of bonded coins that it has. And whether you are in the first phase or the second phase of PBFT, you remember from when I described it at the beginning, you wait for a majority of pre-votes or a majority of pre-commits to eventually commit. A very other extreme example of a system is Hyperledger Fabric. This is a well-known, and we'll be using this Hyperledger Fabric often throughout this tutorial. It's an open source resulting from a consortium of different companies, including IBM, Intel, SAP, and several others. I'm going to illustrate at a high level how they take an optimistic approach. So they're going to execute first and then order and validate that the order is consistent with this execution order. And the basic operation we have is read and write operation. So we basically are looking for read and write conflicts. What's interesting here is that Hyperledger Fabric supports non-deterministic execution. So you might have code that is non-deterministic and it still supports it. As we will see later, other systems assume that the execution must be deterministic. So in this case, I'll illustrate things using, again, our 3 different types of nodes. We have clients. They represent applications, and they're going to issue transactions that need to be executed. There are going to be endorsers, and those are execute the transactions and then validate that the transactions were actually ordered in the same and resulted in the same results as was the execution. The endorsers maintain the blockchain ledger, and each application has its own set of endorsers. So we'll have different applications, each of them with its own set of endorsers. And they know the rules. I can specify the rules for the endorser. So I might have various endorsement policies depending on whether I trust the endorsers or not. I might require a majority of the endorsers to agree on a certain value. And this is especially noticed because we are having non-deterministic executions. Finally, there's an independent set of orders. Their job is to execute the consensus protocol, and they establish the order on the blocks and hence on the transactions. The orders just order things, yeah? They do not maintain the blockchain ledger or the smart contract or whatever And they can also, it's pluggable. So you could use, if you assume that the orders might be malicious, you can use PBFT. If you assume that the orders can only crash, then you can use Paxos. Let's look at an example. Here we have 3 different applications, the green, the blue, and the yellow. Each of them has a set of endorsers. You notice that the number of endorsers depends on the application. So the green has 2, while the yellow has 4. And then we have a set of orders, and they do not have a copy of the ledger. The ledger is available at the endorsers, but not at the orders. All the orders are doing is to execute transactions, and that's it. Sorry, is to execute the order, to establish the order in which the blocks should be maintained and the transactions should be executed. The endorsers are the ones who are going to execute the transactions. So if we have various requests coming, you basically, a client sends it to the endorsers execute it and return the result of the execution. Notice the execution is happening first. Now, the various applications might have different endorsement policies. A client receives all the results from the endorsers, and based on the policy decides what to accept or not to accept, and then send them to the orders. Now the orders are going to execute a consensus protocol that establishes the order among the various requests that are coming from the different applications. So an order is established, and that order is sent to the various endorsers. The endorsers validate that the transactions are executed and are resulting in the correct answers according to the execution that had taken place. And once that is validated, they have to establish if all read-write conflicts have been executed in the right order. Once that is done, it is executed and we are done. Of course, we can have a problem if there are lots of conflicting transactions. They access the same record and one of them is a write. So write or write read. These are the standard things. So for example, if we had in this case, the green application was writing record A and the blue and the yellow were both reading record A. Now we have a conflict. So once the order is given, then the endorsers need to establish what are the conflicting transactions, and there is a conflict between the write and the green write and the blue read, and the green write and the yellow read, and so those are aborted. Notice in a way it's because the 2 reads were executed on the initial state. They do not reflect the state of this write operation. So the write operation was ordered before them, and you have an inconsistent behavior. So as a result, Hyperledger in its basic form shows poor performance when there is a lot of conflict among various the workload has a lot of contention. Now, there have been, Fabric is actually quite popular, and as you see on this slide, there have been lots of innovations and ways in which to improve the performance of Fabric. And you'll notice these are all 2019, 2020, so very recent results. So for example, with Fabric++, you it tries to abort transactions early that can never be reordered, so you avoid write-write conflicts, and reorder transactions after the ordering phase, so that if you have a write read, since the read was reading the initial value, we can switch the order and we end up with a read write, so that improves performance. Alternatively, with Fabric Sharp, it used also early abort of transactions that can never be reordered, and presents a reordering technique that eliminates unnecessary aborts, because you can take advantage of some of the semantics of the read and write conflicts. With Fast Fabric, it uses various different data structures and caching techniques, parallelizes the transaction validation pipeline, and there is an execute order execute fabric, where basically there is both a pre-order, which is what we saw, and a post-order execution. And the post-order execution is added after the validation phase to re-execute the transactions that were invalidated due to the read-write conflicts. I want to emphasize again that for Hyperledger Fabric, the execution of the execution of the transactions does not have to be deterministic. It can be non-deterministic. What you've noticed I've been kind of alluding to is that if we can capture the order in which the reads and the writes by the different transactions are being issued, we can actually take advantage of this to improve performance. And this is a notion that we are familiar with in databases, which is a serialization or a dependency graph. So a dependency graph basically exposes the ordering dependencies or conflicts between transactions. So for example, we have various transactions here, T1 through T5, and in each case we have the read set row. For example, T1 reads A and writes A and B. Then they are going to be ordered, and the order now will be captured between the different dependencies that arise between the different transactions. So for example, in this case, we have T1 was executed and it wrote A and B, and then T4 read B, and it follows it in the order. Left is, this is the head of the blockchain. So as a result, T1 must be executed before T2. Likewise, T5 writes T3 writes E, that is read by T5, and T2 writes D, that is read by T5. That is written by T5. So in this case, we have T5. What does T5 do? T5 reads E and writes D. So as a result, we have T3 that writes the value that was read by T5, and T2 writes the value that was written by T5. So there is an order. T1 must be executed before T4, and T5 must be executed before either T3 or T2. But T2 and T3 can be executed in parallel, and T1 and T5 can be executed in parallel. So again, going back to this model where we have clients, orders, and executors, but in this case, we're going to order first. So it's a pessimistic approach. You issue the transactions, you send it to the orderers, it finds an order among these things, but not only it finds an order among the transactions, it creates a dependency graph. And the dependency graph with the order is sent to the executioners, who are going to determine how to execute the transactions. Let me go into a little bit more details. So we have the ordering phase. A client issues a request. This request arrives at one of the orderers. It executes a consensus protocol among the different orders to come up with an order, and it waits for a number of transactions to arrive to create a block, creates an order among these different transactions, as well as a dependency graph. The new block with the dependency graph is then sent to the executioners, and the executioners independently receive the these different blocks with the dependency graphs. Notice we have here two applications. We have the green application on top and the blue application on the bottom. Each of them has an identical set of transactions in some order. They are going to be executed in that order, one by one. And what we do is we can execute now in parallel, because the two different transactions that can be executed in parallel, these two can be executed first together, this one and this one, and then we can, once these two are executed, then we can execute all of these three in parallel together. Once this is done, all the different operations are sent, all the different results are sent, the blocks are sent to all of the transactions, and a new block is added to the blockchain because it has been executed at all the sites. This works as long as all the dependencies were within each transaction, within one application. If you recall in the previous exam, on the previous slide, there was a dependency among the blue transactions and a dependency among the green transactions. But what if there is some dependency between transactions of different applications? Now, the agents of these applications cannot execute transactions independently. So what we need to do is, if there is such a dependency, for example, from 3 to 7, from a green to blue, then we need to send messages as soon as the execution of each transaction is completed. So you send it out to everybody. So if anybody is waiting for some dependency, they become aware of it. Of course, the number of messages exchanged becomes very big. Alternatively, we can send messages when the execution results are needed by some other transaction. So it's a difference between a pull and a pull. And in the paper, we actually explore the trade-offs between these two different approaches. So in general, we have a pessimistic and an optimistic approach. You either order first and then execute, or execute first and then order and then validate that the execution was done in the right way. With Hyperledger Fabric, it supports non-deterministic executions. It executes first, and then, because it does not submit transactions with inconsistent results. If you have different results, the policies are going, the endorser policies are going to result in excluding those. On the other hand, if we have high contention workloads, an approach that is optimistic suffers from that. And actually, that's very similar to behavior in standard database systems, which are trade-offs between a locking approach and an optimistic approach. On the other hand, if I use a pessimistic approach like Power Blockchain, which is executing the order first and then the execution, but taking advantage of the dependency graph to improve the performance, in this case, we are supporting high contention workloads. The trade-off is that we cannot support non-deterministic executions because it validates the non-determinism at the end and will abort the transactions after all the work has been done. So this dichotomy is very interesting and reminiscent of things we've seen before. So in general, we have 3 different known architectures. At a high level, it's order, execute, or execute order. When you execute order, you need to verify at the end. If you're doing order execute, then if you generate a dependency graph, you can support the parallel execution of transactions. One big advantage of an optimistic approach is that you can actually support non-deterministic executions. On the other hand, a pessimistic approach, which order first, supports high contention workloads. Okay, we'll take a break now and we'll continue after the break.